Lecture 7 today. We are continuing to review things, as well as doing some new things. We're going to talk more about logs, in particular limiting behavior of logs. We will do another proof here. It is a different kind of proof than what we did last Friday, but it's worth doing. We'll look at some application of logs, the log plots, the important kind of application of logs. Then we'll get back into trigonometry, sinusoidal functions, inverse trig functions. That'll carry over into lecture B, sinusoidal modeling, and then we'll start polynomial functions. For the completion assignment due Wednesday of this week, I am assigning it from section 1.6, which includes polynomial functions, but there's other stuff in there that we won't have time for today. So it won't be all the types of problems that you encounter in that section that's due Wednesday, but more will be assigned for that section for Friday's class. All right, so let's look at this other proof. So last time we proved a property of logarithms. I called it the product to sum property. The log of a times b was the log of a plus the log of b. So that's an algebraic kind of property. This is really more of a limiting property. And I know I said after Friday I was probably only going to do the base e logarithm, the natural logarithm. But I changed my mind over the weekend. And I decided this proof would be easier if we do log base 10, the common logarithm. We want to show it's unbounded, both above and below. Now you have some reading in the appendix about what it means for a function to be bounded and unbounded, so I'm going to elaborate on that. A little bit more specifically, we want to prove a couple limits. We want to prove the limit as x goes to plus infinity of log of x. This means log base 10 for us. Common logarithm, and we don't bother putting the subscript there. If that goes to infinity, and the limit as x goes to 0, remember this plus sign means from the right. So you're letting x approach 0 through positive values from the right. This plus really doesn't necessarily always mean positive values. It really means from the right, from the plus side, so to speak, whatever number's there. But that goes to minus infinity. I'm going to prove both of these in one proof. Okay? How? What's the goal here? Let's think about the one where we prove that goes off to plus infinity. Remember I've said, and this is a concept you should understand for the first exam, that for this to be true, it means the graph of the function should get above any horizontal line, no matter how high that horizontal line is. Log base 10 of x goes off to infinity. It's got an x-intercept of 1, but it goes very, very slowly. It goes so slow, if you graph it on your calculator or with Mathematica, it's going to look like it's like almost horizontal if you go out far. Okay? It grows very, very slowly. It seems like it has a horizontal asymptote. But in fact, it gets above any horizontal line, no matter how high. It'll, for example, eventually get above 100. You go way out here. Every time you've gone way out here, finally it gets above 100. How big does x need to be for it to get above 100? This is just some scratch work, so to speak. I want to find x of log base 10 of x is bigger than 100. Think about the equivalent exponential equation. That would be equivalent to x being bigger than 10 to the 100. Essentially, I take both sides and make 10 the base, raise 10 to both of those powers, and the inequality stays the same direction. And over here, the 10 to the x and the log of x are inverse functions, so they simplify to just x. That's a Google. And by the way, the number Google is spelled differently than the search engine Google. The number Google is spelled G-O-O-G-O-L. Does anybody know the story about how the number Google got its name? Some mathematician thought about this number and asked their child, what should I call this number? And the kid said, a Google. And so the name stuck, okay? One with 100 zeros in it. More than the number of atoms in the observable universe. That's how big it is. That's how far you'd have to go for log base 10 of x to get above 100. Whoa. Imagine if I made this 1,000,000. I'd have to go past 10 to the million power. One with 1,000,000 zeros after it. Have you heard of a Googleplex? Anybody? Shake your head. Nobody's heard of it? Well, a couple people shaking their head. What's a Googleplex? A Googleplex is, if I recall correctly, actually I'm not guaranteeing this is right, it's 10 to the Google power. 10 to the 10 to the 100, which you ordinarily would not bother writing parentheses for. It's a 1 with a Google zeros after it. If you were to write it out, those zeros would go past the edge of the universe. I'm serious. That's how far they go. To get above a Google, you'd have to go past, or to get above, get above a Google, you have to go past a Googleplex. Wow. This kind of thinking is the gist of the proof of this part, at least. A similar kind of thinking, what it means to go up to minus infinity as x goes to 0 from the right, is it's got to get below any horizontal line no matter how low, by taking x close enough to 0. Let's see the details now. Suppose m is positive. What is our goal? To prove this. M is going to represent the horizontal line that I want to get above. Y equals m. M could be really, really humongous. It's arbitrary. It doesn't matter how big it is. And I'm going to also let negative m, y equals negative m, be the horizontal line I'm trying to get below as x goes to 0 from the right. The goal is to find a quote-unquote large number b, though it actually doesn't have to be large, and a small number a, though it actually doesn't have to be small, so that log of x is bigger than m when x is bigger than b, and log of x is less than negative m when x is between 0 and a. So coming back to this picture over here, this is like my m right there, and negative m then would be down here. I've got these horizontal lines that I'd like to get above and below. A Googleplex right there, that would be like my b. And some other really tiny number over here, really, really close to 0, that would be like my a. Really small means really close to 0 in this context. If I want to get below negative a Google, how small would a have to be? It would have to be 10 to the negative 10 to the 100 power. 1 over a Googleplex. You can't imagine how small that number is. But it's not 0. How do you finish the proof? Well, essentially doing a thought process similar to what we did over there. You let b equal 10 to the capital N power and a equal 10 to the negative m. Coming back over here, did I do that? M was 10 to the 100. B was 10 to the 10 to the 100. 10 to the m. That's n there. And a here, by symmetry kind of, has to be 10 to the negative m. In this case, 10 to the negative of 10 to the 100 power. So now it's just a matter of using facts about inequalities to finish this, based on letting b equal this 10 to the m and a equal 10 to the negative m. If x is bigger than b, which is 10 to the m, then take the log of both sides. That means log of x is bigger than log of b, which is log of 10 to the m, which is m. On the other hand, you can do something similar with the a. If x is between 0 and a, x is between 0 and 10 to the negative m, then take the log of everything. You don't have to worry about taking the log of 0. The log of 0 is technically undefined. Just take the log of these two things. Log of x is going to be less than log of a, which is going to be negative m. That actually does it. Praise the Lord. Okay? It may not really seem like we're necessarily done, but we actually are. This is a rigorous deductive proof of both of these facts here. The individual steps themselves are not really that hard. It's the putting it together, thinking of it in the first place, and then putting it together that's the hard part. Understanding what the strategy should be, first of all, and then realizing when you're done, that's the hard part. No matter how high m is, I gotta figure out how big b should be so that my graph is above that horizontal line when x is bigger than b. And conversely, no matter how low negative m is, I gotta figure out how close to 0 a should be, so that if x is even closer to 0, then log of x is less than negative. That's what I showed. Okay. Again, these things are difficult. And it's not something that we're going to just do once and stop. We come back to these ideas over and over again to help them sink in. Pretty much everything in math is not something you can get completely just from listening to somebody talk about it for 10 minutes. Right? You're not going to get it completely unless you work at it, think about it. It's just like with sports and playing music. You're not going to get better unless you practice. Right? And you shouldn't necessarily expect something to click right away completely. Or maybe it sort of clicks and you're just not sure. So you got to come back to it later and think about it and work with it. Talk about this more in other classes as well. Here's an application of logs. So that previous slide was theoretical. Now we're getting into some applications. You don't have to write down all that data or make those graphs. It's probably better for these graphical slides to just listen. So we've looked at these data before. By the word data is actually plural by definition. So you should say these data instead of this data, though I sometimes make the mistake of treating it like singular as well. So I won't mark you off if you don't treat it like you should and treat it as plural. But just realize it is plural. Datum is the singular. So we looked at these data before, plotted it. The US GDP in trillions of dollars is a function of the year, these red dots that you see. And we did a linear fit initially. It follows the general trend okay. It's not too bad. But it's not ideal because when you plot the residuals, which are errors, they're essentially how far above or below the line these red dots are. For example, this red dot a little bit below the line for 2016, so its residual is negative. This red dot's kind of far above the blue line, so its residual is kind of a large positive number. Those residuals represent the sine distances vertically from that blue line. And it's not random. There's kind of a trend. You might say it's a nonlinear trend of the residuals like this. You might also just say, well, it's not random because we got 7 positive residuals in a row there. That's not likely to happen by chance. You gotta say positive. 7 negative residuals in a row. It's not likely to happen by chance. You want randomly scattered residuals. Because you want those to be random. You want the line of the curve to truly match the pattern of the data. Then we saw that in exponential growth it was better. That blue curve is a curve. It's not a straight line anymore. It is an exponential growth function. And it does better because the residuals are more random. Though I did mention that it's sort of doing worse over here in later years compared to earlier years. And that's to be expected in this kind of application because, when you try to extrapolate, the future is uncertain. If you try to use this for 2019 or 2020, it could be way off. You shouldn't expect to be able to extrapolate beyond there too far, though people try. People probably would try to use this model to predict the GDP for 2019 and 2020. I definitely would not use it for 2025. But again, the residuals are a little bit more random. A couple positives, then a negative, then a positive, then a negative, then a couple positives, then a couple negatives. A bit more random. That's better. Is there another way we could be pretty sure that we're looking at an exponential growth function rather than a linear growth function? You can make a log plot. This is the point here. It's an application of logs. You can take the log of the y values. That's what I did here. Log base 10, actually. What were those y values? I will come back to this slide in a second here. Those y values are generally speaking between 14 and 21 trillion dollars. I'm taking the logs of those numbers. Look, these are between 1 and 2, which they would have to be because the log of 10 is 1 and the log of 100 is 2. Our numbers between 10 and 20, they got to be just a little bit bigger than 1 as they are. And if you plot these data, where the horizontal axis is time in years, and the vertical axis is this log of the GDP, then those points seem to be more along a straight line. It's a really important application of logs. You're going to see this applied in science, in economics, all over the place. People do this kind of thing all the time. That's a bit more of a straight line pattern, and in fact, if you plot the residuals there, you do get some randomness, and in fact, it matches the randomness from the other slide of the exponential fit to the original data. A couple positives, then a negative, then a positive, then negative, then a couple positives, a couple negatives, then a positive. And the relative sizes are about the same too. Previous slide, we matched the original data with a curve that was an exponential growth. On this slide, we're matching the transformed data. This is the log of the GDP axis with a straight line, and the residuals follow basically the same kind of random pattern. That's good, actually, if you want to use an exponential growth because of the following slide. Why does this work? This is kind of detailed here. You probably want to start taking notes now, if you haven't been. We're given some data. Oh, I hate when it does that. I use a Mac. When the PowerPoints get transferred to PCs, if I do dots inside my math mode, on the PC it makes these arrows. Those arrows are not supposed to be there. They're supposed to be dots. We might be able to fix it, actually. No, okay. It's not letting me. There's supposed to be dots there. You got n data points. You're wondering, are these data points exponential? That's what you're wondering. You make a log plot and see if the log plot is linear. If it is, that means the original data is exponential. One of these data well modeled by an exponential function. There again is our form for an exponential function. Here's the theory behind it. What you do with this is you take the log of both sides of this equation. The log data, well, you take the log of the y-coordinates of the data first. And again, this should be a dot. See what I'm doing there? I'm creating new points whose x-coordinates are all the same as the original x-coordinates, but whose y-coordinates are now different. They are the logs of the original y-coordinates. If you do the same kind of thing in a sense with this function, if you take the log of both sides, and I am taking the log of both sides of the equation there, here's what you get. So again, keep in mind the context here. Think with me as you write. You got some data points, two-dimensional bivariate data. You're wondering, does an exponential growth model fit these things? What you do is you create new data points whose first coordinates are all the same and whose second coordinates are the log of the original. I'm choosing the log base 10. If the claim is if those follow a straight line pattern, the original data are going to be exponential. Here's what justifies that. Pretend it's well modeled by an exponential. Take the log of both sides of that equation. That's what I'm doing here. Then use properties of logs to rewrite this thing like this. How am I using properties of logs? I hope you can see it pretty easily. This is a log of a product, a times b to the x. Therefore, it's the sum of the logs of each thing individually, log of a and log of b to the x. Pretend there's a b to the x in there. Then use the property that you can bring the exponent down in front. I did 2 steps there. Now look at this equation and just think. What does this equation represent? It's really representing the quantity log of y as a linear function of x. Right? Because that's a constant. A and b are constants. Log of a is a constant. Log of b is a constant too. There's your vertical axis intercept. There's your slope right there. Because it's being multiplied times x. So when your data are well modeled by an exponential function, the log of the y coordinates will be a linear function of x. That's why the method works. Whereas the first equation over here represents y as an exponential function of x. The second represents the log of y as a linear function of x. So if you take the log of the y coordinates of all your data points and plot it in a new graph where the vertical axis is the log of y, the data will follow a linear trend. A linear function of x, x to the first power. Mm-hmm.
And then if it isn't linear, it wasn't exponential.
Right. If when you do this, it's not linear, then the original data is not exponential. That's true. Thanks. Okay. So this kind of, again, this kind of application comes up all the time. You're in science, engineering, economics, psychology even, business. People use this for business. This kind of thing is done all the time. You might have also heard of log-log plots. This is a log plot idea. There's also a log-log plot idea where you take the log of the y's and the log of the x's. We'll talk about that more on Wednesday. All right, we're going to go back to trigonometry now. And the goal here is to review the trigonometry as quickly as possible so that we can do a little sinusoidal modeling, as you did on your homework for today. And we're going to try to find a formula for a graph that's going to look approximately like this. It's going to be a periodic function. It's going to look approximately like this. I don't remember exactly what points it goes through yet. We'll see that in another slide. So that's something you should have worked on for today anyway. So this should be review, although it's not an easy thing for most people to do. But before we get there, we should review. The unit circle definition of cosine, sine, and tangent I will add today, a little bit more detailed than last time. So there again is the unit circle. This is the best way to think about cosine and sine if you want to get to thinking about what their graphs look like as fast as possible. Yes, you should know about right triangle trigonometry, SOHCAHTOA. That is necessary use sometimes when you've got a right triangle in the picture. But as far as finding the graphs, and therefore modeling oscillatory behavior as quickly as possible, it's best to start with this unit circle. I like pretending that black dot is a bug, a really smart bug. Maybe it flies around, it lands over at the point 1, 0, and then you give this bug some directions. You give it a number. If you give it a positive number, the bug starts walking counterclockwise around the circle. If you give it a negative number, it goes clockwise. And how far does it go? Whatever number you give it, that's how far it travels. Say you give it the number 1. Remember, it's 2 pi units around the entire circle. It's about 6.28, right? 2 pi. What's 1 unit of distance? Well, you can eyeball it to be approximately about like this long right there. That's going to match an angle of 1 radian. That's how radians are set up. As an angle measure, it's actually the most natural. It's more natural than degrees. When you've got the unit circle like this, the radian measure of a given angle will equal the arc length of that piece of the circle. Right there. Whatever the radian measure of that is on the unit circle, that's the same as that length. It's the same as the distance the bug walks. And then when the bug stops, based on the number you give it, say 1, then the bug is smart enough to figure out what its coordinates are, at least approximately. Or you are, you're looking at the bug. The first coordinate is the cosine of the number you gave the bug. The second coordinate is the sine. And that's fortunate, it goes in alphabetical order. Cosine and sine. Say this is the unit circle. Say this is an angle of 1 radian. The x-axis there is 1. That's going to be the same as this arc length. That's also going to be 1. The coordinates of this point, by definition, the first coordinate is the cosine of 1 radian, and the second coordinate is the sine of 1 radian. And we definitely want to use radians for calculus. Okay? It makes derivatives of trig functions much, much simpler if you only use radians. It's not that you should forget about degrees. You should always be able to convert back and forth between degrees and radians if you need to. 1 radian, to figure out its degrees, you'd multiply by 180 degrees over pi radians. That's the conversion factor. The radians will cancel, and the answer is 180 over pi degrees, and then you can approximate it with your calculator. And I think it's like about 57 degrees or something. So you should always be able to go back and forth, but in terms of calculus, and in terms of the most natural definition of the trig functions, you want to use radians because the angle measure matches the arc length. And again, that helps you figure out what the graphs look like, because you can easily figure out when is the cosine and the sine positive and when is it negative. The blue is the sine. Okay, that's easier to think about here first. It's not really the vertical distance of the blue line. It's its displacement, where when it's above the axis, the horizontal axis, you think of it as a positive displacement, and when it's below the axis, you think of it as a negative displacement. So the blue graph is above the horizontal axis when theta is between 0 and pi. 0 to pi, 0 to 180 degrees. And it's negative when you go past pi down to the 3rd and 4th quadrants when theta is between pi and 2 pi. Radians. That's 8 degrees. Okay, I said 0 to 180 degrees. That's what I said before. It's negative when you're between 180 degrees and 360 degrees. On the other hand, the cosine is the displacement of the red line. So again, that's why you want to think of this graph sideways to see it as a true graph of the cosine. It's measuring the horizontal displacement positive when your point is over in the 1st and 4th quadrant, negative when it's in the 2nd and 3rd quadrant, because it's the first coordinate of that point. Since this is the unit circle, you also have the case, since the equation of the unit circle is x squared plus y squared equals 1, that's going to mean cos squared theta plus sine squared theta equals 1 no matter what. And this is standard notation to use, though it's not ideal notation. You should make sure you understand what this really means. It really means cosine of theta quantity squared plus sine theta quantity squared equals 1. That's what this notation means. When you think about this function, you do the cosine first and then you square it. When you think about this function, you do the sine first and then you square it. The order of operations matters. If you meant to square first and then take the cosine, you'd write it like this. That's square first, then take the cosine. When the 2 is put like this, it means take the cosine first, then square it. I like to try to emphasize putting parentheses around the input as well, though in books that's not always done. To emphasize that that's the input of your function, I think it's a good idea. What about the tangent function? Tangent of theta is sine theta divided by cosine theta, and I will go ahead and put the parentheses even though I didn't initially. It's the length of the, well, the displacement of the blue line divided by the displacement of the red line. Both displacements are positive when you're in the first quadrant. So the value of the tangent in pink is positive. They're both negative when you're down in the third quadrant, so the value of the tangent is positive over there when theta is between pi and 3 pi over 2, which is this part of the graph right there. They have opposite signs, the red and the blue lines, their displacements. When you are in the second or fourth quadrant, that's where the tangent is negative. Right there, and also over here. And the tangent graph, the pink graph, has vertical asymptotes. Why? Well, you'd be dividing by 0 if cosine is 0. Wherever cosine is 0, wherever the red graph down here is 0, like at pi over 2, 90 degrees, the tangent is undefined there, and you do have a vertical asymptote. We're more concerned about cosine and sine, though, than tangent. Tangent also turns out to be the length of this pink line that you see here, sine length, the displacement. Because tangent also equals the slope of the black line, and the if you think about it in terms of rise over run, this run is 1 because it's the equal circle. Think about drawing a triangle. Let's take our break, then we're going to come back to the graphs after the break.